And this fragment also has several problems. Gain from 3.2 primarily related to units and zero divisors. Let me begin with exercise 1-1, page 68. So we have A, which is an element of a ring R, and A is a non-zero element, and A is not a zero divisor. Is not a zero divisor means multiplying A by any non-zero element from right or left. We will never produce a zero. I will solve for you only A of this exercise. They want to show that AB equals AC implies B equals C. Cancellation by a non-zero divisor is possible. B is similar. Similar, but up to BA equals CA. We do not assume that the ring is commutative. We don't need that. Or how do we prove that? We simply add negative AC to both parts of equation, rewriting the equation as, so rewrite the equation adding negative AC to both parts. As AB minus AC equals 0 in the ring. Now we can factor A out. This by distributive law, this is A times B minus C is 0 in the ring. And now we use that A is not 0, otherwise this of course holds whatever B and C are, if A was 0, and A is not a zero divisor. So A is not 0, A is neither 0 nor a zero divisor. Meaning multiplying A from the right or left, in this case we multiply from the right, by any non-zero element of the ring, we will not produce a zero. Here we do produce 0, and that means that we multiply it by 0. Implies B minus C is 0 in the ring, which means B equals to C as required. If A was a zero divisor, we would not be able to deduce from the zero product that one of the factors was 0. It may happen that A and B minus C are both non-zero, while the product is 0. It does not happen simply because A is assumed to be not a zero divisor. That condition is crucial. Another problem in this connection, 17, on page 68, tells us that no unit is a zero divisor. Namely, R is a ring with identity. One R in R, and if an element is a unit, then U is not a zero divisor. Here's how we prove that. Well, since U is a unit, U inverse exists, so since U is a unit, there is, that is a definition of unit, U inverse an element of R such that U inverse U inverse, same thing, which is 1 in R, the identity in the ring. Now, assume UV equals 0. We want to deduce that V is 0. U is not a zero divisor. No element V, which is not 0, will give us 0 as a product. So we want to deduce that V is 0 in the ring. We multiply this identity by U inverse on the left. U inverse UV equals U inverse multiplied by 0. Now we know that multiplication is associative, so U inverse is 1, this 1, and 1 times V is V. Oh, let me write one more row. We write it as 1 R V equals, and anything, whatever it was, U inverse or somebody else, any element of our ring multiplied by 0 in the ring is 0. Or now we can identity multiplied, that's the requisite property of identity, that multiplied by any element of the ring is this element. So we did indeed deduce that V, well, as we wanted, we deduced that V is 0. Thus, UV is 0 implies V is 0. In fact, we also, this is formally not the end of story, because we need, and this is very similar, we prove that VU is 0 implies V is 0. We definitely need the second one in order to conclude that a unit cannot be zero divisor, because it may happen that we multiply some element from the left, get 0, this element must be 0, but from the right the situation may be different. We multiply by some v which was not 0 and produces 0. Such units, such zero divisors which are only left or only right zero divisors do exist. In contrast, a unit has an inverse which is both left and right inverse. So take care, look carefully at the definitions in the book. Zero divisor may be a zero divisor only from the right or only from the left. Unit is a unit from both left and right with the same inverse. So here is yet another problem from the set, a slightly more tricky problem, 38 on page 70. In this exercise, R is still a ring with identity. And A and B are two elements in R. Neither A nor B is a zero divisor. Now I need to prove the following statement. If AB is a unit, then both A and B are units. Here is how I start the proof. I will prove only one, another one is similar. So I will prove A is a unit. Now, AB is a unit implies the existence of an element C, so since AB is a unit, there exists C in the ring, the inverse, such that ABC, AB times C equals identity. In fact, also CAB equals identity, but I will not use it. So C is the inverse for A and B. Because I deal only with A, I will need only this one. So now from here, we immediately get that A times BC is identity. However, that is not the end of the story. The difficulty is not that, of course. We're almost there. There is an inverse. But now we have to prove, so we are left to prove that BC times A is also identity. That BC is indeed the inverse for A. We wanted to prove that A is a unit. So we kind of found the inverse, but only from one side. Now we need BC now to be the inverse from the other side as well. For that, that will follow from the following proposition. F, so there are two statements, x, y, is identity in the ring, and x is not a zero divisor. These two imply yx is identity in the ring. That is a difficulty. We do not assume that our rings are all commutative. There are examples, matrices, 2 by 2 matrices in the first place, but there are many others of non-commutative rings, so we cannot assume the rings are commutative. Now we already have one of them, we need another to prove another one. That will follow from this proposition. Indeed, let us check that. We have A for x, BC for y, and A is given to be not a zero divisor. So the first factor is not a zero divisor, is given. Then we can interchange y and x. It is only for inverse, it is not in general. In general, that's a difficulty. You cannot interchange the factors in an arbitrary, non-commutative ring. Here's the proof. So it is clear that this proposition will immediately give us this and finish the exercise. So now we need to prove only this proposition. I wanted to do it separately with x and y, making it a little bit clearer, because BC is a product of two of them. We don't need that. Alright, we have xy is identity, and we multiply xy identity by x from the left, from the right. We get x, y, x is identity times x is identity. So this is a property of identity, although for arbitrary elements x, y may be not equal to y, x, identity multiplied from right or from left by any element is this element. So this is two-sided neutral element for the multiplication. Two-sided neutral element for the multiplication. Alright, we add negative x to both sides and get it xyx minus x is 0. A good thing is that we multiplied from the right, but we can now factor x out from the left. Here is x alone, and identity x is same thing as x identity, which is x. And here we have x from right and left. So we can factor out any one as we like. X, yx minus 1 identity is 0. Now we use the fact that x is not a zero divisor. So x multiplied by anything from right to left is going to be 0 only if the factor was 0. So since implies since x is not a zero divisor, that yx minus identity is 0, or yx is identity, adding negative identity to both parts of the equation. 0 is, of course, everywhere 0 in the ring, not just 0. So we proved the proposition. We wanted to switch it. We had xy is 0 with an extra condition, not a zero divisor, and we wanted to switch it yx with the same y is xy is 1. We wanted to switch it, yx is also 1. We did it. So that is because 1 commutes with any element, and we could multiply from the right but factor out x from the left. So we proved that we can switch this under the condition that x is not zero divisor, and that is exactly what we wanted to prove here in order to get that A was a unit. It is similar about B. I will not do that. With appropriate changes, you use this one, you change everywhere right to left, left to right, and prove that B is also a unit in the ring. So I wanted to show you this problem because I wanted to show you this trick, and besides this trick, I wanted to attract your attention to non-commutativity that may be quite subtle. We sometimes can do that, but in many that definitely requires an extra consideration, unless it is given that the ring was commutative, which is going to be the case only in chapter 10 from the book, so we have way to go till we assume all rings are under consideration to be commutative. Thank you for listening.